We've got a really exciting program for you tonight. First of all, we have Renzo, who's going to be talking about Clojure's Reducers, which is a really exciting new library for Clojure. And then next up is Chris Jenkins, who's going to give us a talk on the history of Lisp. So just a bit of admin before we start. The London Clojure dojos, I don't know if I recognise a lot of you, but is there anyone here who hasn't been to any of the dojos before? Okay, quite a few of you. There's 2 dojos in London, one at ThoughtWorks, which is the last Tuesday every month, and then one at Forward, which is the first Monday of every month. And they're a fantastic place to, fantastic environment to come and learn Clojure in a very supportive, non-judgmental environment where people get to do all sorts of fun stuff. I didn't make the last one, but Phil, I think there was something to do with landing aeroplanes or flying aeroplanes with Clojure, and some sort of fantastic exercises which you don't have to do on your own. You're with a team of people of mixed Clojure ability, and it's a fantastic way of getting your hands dirty with Clojure. So thoroughly recommended. And if you want to know more details, details will be at londonclojurians.org. There's got a huge in-your-face QR code there, so if you take a picture of that will give you all the details. You don't have to jot it down. The mailing list at that website. But thoroughly recommended, especially if you're new to Clojure. It's a fantastic way of learning it with some really exciting challenges. So do recommend you attending that. Now, next up is a Clojure training course. Now, those of you who've been looking through the Skills Matter website searching for the Clojure training, your search is over. We're very, very happy to announce that there's going to be a 2-day fast-track training course in Clojure starting in June, Thursday 20th and 21st of June. And this is a subject very, very close to my heart. I'm passionate about Clojure in organisations and commercial adoption of Clojure, and what's been holding a lot of people back has been the lack of training and the concern of starting a new Clojure project in a company where there's a fear that the Clojure people, the Clojure gang, will go and potentially move off and do something else, and then kind of you're left, how do I get my staff to learn what those guys have done? So having a Clojure training course is very exciting, and if you want more details of that, you can talk to Bruce or come see myself or contact Skills Matter. If you've got any questions or feedback or any ideas of explaining Clojure to brand new beginners, then do come and speak to me afterwards, perhaps in the pub. John Stevenson's not with us tonight, but he's launched a new ebook today, and I'm very excited to promote that. The link is there, and it's a new book called Clojure Made Simple. I don't know. Partly like that anyway, so I'm sure it's well worth it. And finally, if I can just, there we are. You can join us for a drink. Do come afterwards to the Slaughtered Lamb, and we can talk about the talks and the training course and all those other things. So I'll hand over to Renzo now.
Hardcore functional programming, maybe a few patterns in that as well, like extractions of functions and bindings and so on. So it's I thought maybe instead of showing you slides, I'll be showing you some live code with all, of course, the entertainment that will generate when I'll have keystrokes and things wrong. And well, I'll try not to do that, of course. A little bit of introduction about the topic, though, that's necessary. Reducers is a new feature introduced in Clojure 1.5, but it has kind of a very old history. Because we can track back all the attempts to create parallelism, so to introduce parallelism for collections, back to Clojure 1.0 with PMAP. So have any of you used any of those PMAP, PVMAP, pre-reduce, that never entered trunk though, or reducers in their work or their experiments? Or I will... Somebody? Well, anyway, it's trying to solve a problem but maybe the reason why we are using functional languages today is just because we heard that they are going to be very performant in terms of multi-core architectures and scaling up to multi-cores. And we should be able to have that feature right in when we start using a functional language. And so parallelization of collection means I can have an algorithm of some sort operating on collections, and I want this algorithm to go parallel on multiple cores instead of like scale horizontally like Hadoop, for example. And Reducers is trying to solve this problem. As I was saying, PMAP was the first attempt, is in Clojure trunk, is there since 1.0, and it's using a pool of futures, so Java futures, and it operates on the collection by sending one of those future for computation on some of the cores, that the JVM will take care of that. And when the computation comes back, it's up to you to collect the results. If you need any combination of those results, it's up to you to do that combination. So it's useful in many cases, probably. It doesn't work very well if the function is not doing a lot of work. So it works well instead when the function is doing a lot of work. It takes time, so it makes sense to send that function in a future. You go do something else with the code, and then when the results come back, you combine them back. After that, an attempt was done with prereduce. Prereduce was an attempt to extend the concept of parallelization on collection on something else that was not a map operation, reduce operation, of course, in this case. And that was also the first implementation to use fork join, JSR 166 at that time in Java, and now entered in Java 7. So that's available now. You don't need an external jar. But if you have Java 6, you can use it with an external jar. It's quite easy to make it work. And that was a reduce operation, of course, and was operating on mapping Clojure collection on top of parallel arrays that are part of the fork join framework. And so it was not working really for all collection, and by the way, it was not working natively on collection on Clojure. So all these attempts, I think, the author of all these attempts is always Richiki. So I think that the prereduce didn't make it to trunk, or well, no, I think it made it to trunk, but now is deprecated in favor of reducers, which is a better implementation of the same concept. And after that, we had another iteration of the problem of parallelization with PVMap. That, I think, never entered trunk. It's on an external branch that you can still access and see how it is implemented. It's still using a fork join model. This time is using native collection, but not all of the Clojure collection, just vectors. That's, I think, the V parallel vector map. And also, it still requires, from the language implementer point of view, to implement multiple collection operations in that sense. Sorry. If you have a map, you have a parallel map. If you have a reduce, you need a parallel reduce, filter, parallel filter, and so on. So it requires language implementers to duplicate operation on collections. So none of these were the best approach until reducers. Reducers fix almost all of those problems with some trade-offs as well, but introduces a single entry point called the fold, which is essentially a reduce operation. But the difference is that you can join inside this fold all the other operations on maps that should go parallel. So you can combine a bunch of maps, a bunch of filters, all together and give them to this final step, which is the fold, and all of this will go in parallel at the same time. So that fixes the problem of working on native collections. It's worked just fine on anything iSequence on Clojure, and also solves the problem sort of having double operations, doubling up the operations to have them parallel, the parallel version of them. Enough chatting. Let's see if I can give you an idea of what I'm talking about. So I think where we want to arrive is something like this. Parallel reduce of some sort that it has the same semantic as any reduce. So we'll take a reducing function. We'll take optionally, can send them in or not. Well, let's remove the initialization, the seed for the moment. So a reducing function and a collection, and it does some heavy load fork join stuff here. And for the moment, I'm not going to do that. That is what the reducers are doing actually in trunk at the moment. I'm just going to use a normal reduce. And I'm passing just down the two things. And we can prove that this is working just fine. Well, let's create a collection that we can reuse. So of some sort of big thing, and if reduce plus on this collection, we have some result. So it's summing all the numbers up to 100. Fine. So our problem now becomes, how can we attach something? So let's say this parallel reduce is doing some heavy load work underneath. So it's going to parallelize the computation of the collection, is splitting the collection into pieces and sending the pieces to each different course and combining them back somehow. But it's just a reduce. What if we need in our business logic some sort of map or filter? We need to filter out elements. How do we put that concept of how do we tell the core that we don't just want to reduce while we are iterating the collection, but we want to do some transformation on those elements? Well, it turns out that that plus at the end is just something that is taking, accumulator, and it's just doing an operation like this on every element of the collection. And so it should come to no surprise that this should work exactly the same. So we have a function there, and so we can operate on that function. And so we have the accumulator that reduces is passing to us. We have the element. We can do any transformation we want on that element, including, for example, incrementing the element. And now it's a little bit higher, because before doing the reduce of all the numbers up to 100, we are also incrementing them of 1. So we've kind of found a way so that we can inject some other behavior inside that plus. So when that goes into multiple cores, it's going to be parallelized as well. The next step is to abstract away a little bit from this, in the sense, what if I don't want an increment, or if I don't want exactly a plus as the reducing function. It is generically an associative function plus and some unary operation increment to do the mapping. So, well, we can abstract them away. How do we do that? We just, instead of defining plus that way, we can call it map transformation, maybe, trans. We can pass in a map function of some sort, map f, and we can just create a function of, again, 2 arguments, accumulator and element, that instead of just adding accumulator, it's also applying that map function to element, And once again, if now instead of calling plus, we call map trans, and we pass in, what was it? Yes, no, sorry, the increment. We obtained something that is still using the associative class, but we can decide what kind of map we can send in. The same we can do, we can extract out that plus. So we can do, again, map trans of, well, we can leave the map there, but we need another associative function that we need to pass in, and then this is returning, again, a function, but instead of using plus, we use, oh, sorry, associative function. We just call that associative function. So we have a function that is returning a function of a function. Might have forgot something here, right? So now we can pass in a mapping function, not only, but also we can decide what is the associative function we want to use. Right, in this case plus. Still there. Okay, we abstracted away what we can do with this map transformer. Let's see, I have another 5, probably 7, 8 minutes. It's not going to be easy. Well, we are here now. You can do kind of the same thing. I'm not going to show you, but you can do kind of the same thing with, instead of a map transforming, a filter transforming, and the semantic will be slightly different. Instead of applying the associative function, it would do something like, if some predicate you pass me in is true, then you do the associative function to the accumulator and the element. If it's not, then just return the accumulator. And that will just remove the element from the final collection that won't be reduced. All right. So what we maybe don't like about this at the moment is that it's similar to a reduce, but it's not exactly a reduce. Yes, it's operating on a basic collection, but we would like, if possible, to read this like a normal reduce, and we would like to read the collection with an applied increment or a transforming function, like a map, applied to the collection. Sorry, it's really not easy to explain in words, so we are going to do some work now. So it turns out I have 2 ways to apply that map transformation of an increment and a plus to the collection. One is the one I just showed you, which is transforming the definition of plus for the reduce. The other is to go inside the collection and override the concept of reduce for the collection. Why is that? Because since CLOJURE 1.4, reduce is implemented as a protocol. That means that each collection type somewhere is implementing a protocol and is using a specific version of how reduce should work. So we can just intercept that call to the reduce of that collection. That in this case is, what was it? Vector, I think. And if we are able to intercept the reduce implementation of that vector, then we can move that external behavior or additional behavior into the collection. Let's see how it looks like. This is the bit I need to copy-paste, though, because it's going to reify the call reduce protocol, and there's no way I remember how to do that without having a look. So we're going to use the protocol, and this is the way you do it. Let's put that in color. Yeah, we'll have to. So what this function is doing is a function of a collection and some function, which is a transforming function. It takes this collection and transforming function, and it reify the collection call reduce protocol, so that when call reduce is called on collection, and this is what reduce will do, we can introduce a different behavior. So there are a couple of variations of that based on the fact that we have a seed or we don't have a seed, but they are doing the same job. And what they are doing is, when call reduce is called on this collection, instead of calling the vector call reduce, call this. And this is an application of our transforming function, what we called before map transformation, onto the call reduce is returning this function, and that function will be applied instead. Let's see if I can show you how this is going to happen. So, oops, sorry. Can I go up again? I need to see. Oops. So we have add custom reduce. So what we can do is still call our reduce. We can free the plus of all that plumbing that was doing incrementing, the additional incrementing, and we can concentrate on the collection. So we can add a custom reduce to that collection, which is still call, and we can pass in this transforming map that we defined before. So map trans of inc, and we are still there. So this is exactly the same result, except for the seed. But yeah, because depending if you pass in the seed or not, that can be 50-50 or 50-49. But you can make it consistent. It's just because I'm not consistent in this. Oh, by the way, why I'm not making this full screen? All right. So we are kind of close where we want to go, and where we want to go is we are manipulating the collection, but I'd really like to see something like what I'm used to, if possible, and that is possible if I create another function called rmap, and this rmap takes that increment function that we can now extract out of the method, and what is going to take the collection. And it's just doing what we are doing here, add custom reduce of collection, and we are applying, oops, sorry, our, oh, I cannot call that fn. Really? I can try later, but not now. I'm very scared of what can happen if I do that. So our custom reduce collection of, that is coming from the outside now. Oh, sorry. Map trans, and the increment is coming from the outside. So a better name for that would be, what would be? Just the increment, oh, sorry, increment, the mapping function. And, oops, let me see. Oh, I know why. Bear with me. Now there is one more. And with this rmap, we are very close to what we want to see, because now we can write something like rmap of, well, what we are used to is like very close to map increment to collection, but it's just rmap instead of add custom reduce blah 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 blah. So the thing that is called rmap there is the definition of reducer. So it's called reducer because it's a way so that we can do all these things all together, intercept a call, override the call to reduce that our parallel reduce is doing, and inject some additional behavior, some like increment. And I'm not going to show you now, but I can easily, now I don't have the R filter, but I can easily do something like this and compose them in such a way so that when I send them to like multiple cores, everything is operating in parallel. In the actual reducers implement, so reducer is the name of that rmap, rfilter, and so on. The way we use those reducers is by using fold. So that p reduce that I created and is doing some heavy job to do the fork join of the collection is actually what is called, what is fold in reality. And so you will find, if you look at examples, something like this. Or R-fold usually, because it's using the namespace as R. Am I forgetting anything? Well, questions? Or, because I think we are at the end of the 20 minutes of this hacking session. Were you able to follow? Yeah, sorry. At the top. There it is. It's just reduce, really. Yeah. It's just to show you that it's just to show you a placeholder for fold. There is a function called fold that operates on reducers that is taking the collection, splitting the collection into multiple pieces, and then at the end, at the leaf of the collection, sorry, at the leaf of one of those pieces is actually doing a reduce. So it's just to show you that these reducers are called reducers because they have the same semantic as a reduce operation. And so they can be used, instead of using a normal collection, they can be used in place of a normal collection to do the reduce. So what is coming, sorry, if that, maybe that is confusing, but if you open up this closure sources, you'll see the fold implementation, and the fold implementation is just doing some fork join work, and at the end is calling reduce on a leaf, and is combining back. Sorry, one bit that is missing from this, because I tried to simplify, is that the fold is semantically equivalent to a reduce, but it's also doing the combine, which a reduce is not doing. So when all these pieces goes out in parallel, and you are doing map, filter, reduce on them, they come back with the result, and then you need to combine them using some function you provide that is not shown here. So the actual fold is taking a combine function, a reducing function, and a collection. And optionally also the split size, how big you want the split to be. I'll show you an example, also for all the others. Yes, we'll work with fold. Fold takes 3. So it's I think it's also implemented with 2. If you don't pass the combining function, it is using the reducing function to combine as well. So it also can take the 2 parameters. Yes, indeed. For many, for the examples, I wanted to show you this. Where is? All right, yes, and a simple one could be the usual count words. So the first version here is how you can do a count of words coming from a list of sentences in a normal way. So you do your map of those words into a sequence, of those sentences into a sequence of words. You're also doing some lowercase kind of stuff. And at the end, you are doing a reduce on association and many other things, but at the end, you're doing a reduce of an increment on the count to obtain the word frequencies. So I have this many words of this many words, A, the many words B, and so on. And below is how you would implement that with reducers. Except for this monoid thing, that we can have another 1-hour talk about it, which is just an helper function to create a combine function. Except for that monoid, all the rest is very similar to the non-reducer implementation, except for this R map that I had to hand. And instead of using a pure reduce, I'm using fold. So this goes in parallel. And we can also see it running, I think. Word count test. So while we are talking, I'll also run it. And you should see around 3 seconds for the first, 5 seconds for the normal one and 3 seconds for the second one. And it's not long enough, but it's running on multiple cores. Yes, I've got dual core. Yeah. Dual core and 2 pipelines for each core. So if I do this, should be able to see Java going above 100%. That means I'm using more than 1 core.
Is it just using the course in the actual initial?
No, at the moment, it depends on really on the fork join implementation that Clojure is using. So if it's not implementing that natively, like sending threads actually to multiple cores. So as soon as Java supports running on multiple GPUs, that will become a possibility as well. It is. Where it is here. Oh. But it's repeating that many, many times to make it a little bit heavy, computational heavy. And he's working on a vector. I don't remember exactly, but I think that is the reason. Last thing, I was using this. I was using reducers to do some heavy counting stuff on competitions. That is a very good problem to parallelize multiple cores when you have to count all the votes for candidates, and those votes are, of course, 4 million, 5 million, and plus. And you can do that as a normal sequence, but you can also use reducers. In this case, the kind of computation is essentially a reduce, but there are several business logic in between, so that I need to skip some kind of votes if they are above some threshold or if they are invalid. There are several filters, so I was able to combine 3 filters and to pass them down to. Now you don't see that; you just you see the main and this fold by, but the fold by is just using fold here. And my collection has been filtered with all of this reducing filters. So at the very end of that, there is a votes, which is the original collection of this line, I mean. And then I'm applying a chain of 3 filters, reducing filters, and then send that to fold. And that goes in parallel to multiple calls. And this is extremely reducing the amount of time required, down 40%. But there are optimizations I need to do, especially on the Bloom filter. That's now it's not performing well. Well, I/O depends. You need to be fast giving the votes to this algorithm. Yes, true. But that is on Amazon, so it's scaling horizontally, the queuing, and is sending 3,000–4,000 votes per second to this thing. I think I'm over time.